Okay, so this is a joint work with Paata. The inequality is named after Eldan and Gross, which I will certainly reveal later. But first of all, let me give you some background about the Boolean functions. Okay, so we have already seen a lot of notions about Boolean functions in previous talks. In my talk, Boolean functions are defined on plus minus 1 to the n, and the function will take values in plus minus 1. Plus minus 1 instead of 0 and 1. But essentially they are the same. Here are several examples. Well, Boolean function has many connections to many other areas, such as social choice theory. So roughly each Boolean function gives you a voting scheme. For example, this dictatorship function, which just takes any string x to one of these coordinates, xj, then certainly this is a Boolean function. This is so-called dictatorship because this voting depends only on a single person. The so-called majority function says the following: if you have n people in total and each of them votes for plus 1 or minus 1, then you look at the majority of the people who vote for 1 or negative 1. So, in other words, if the sum of these coordinates is non-negative, then the outcome is plus 1. Otherwise, it's a negative 1. This is the majority. The so-called tribe function is as follows. You have n people in total, and you can divide the n people into s tribes. Well, each tribe so you divide this n people into s tribes. Each tribe you have exactly t people. Then the voting is as follows. If you can find at least one tribe among these s tribes in which all the people vote for you, okay? If all these t people in this tribe vote for you, then you win the election. So this is a so-called tribe function. These are the three very typical examples of Boolean function, which will be mentioned later. So in the following, I will consider several notions about the Boolean function. One very basic concept is so-called variance. And throughout, I will equip the discrete hypercube with the uniform probability measure to define variance here, as well as LP norm that we will see later. So in particular, I define this variance here for any function on the Boolean cube. So in general, you don't really have to consider a function that takes values in plus minus 1. You can consider function taking values in real numbers, complex numbers, or even more general Banach spaces. But here, if you consider Boolean functions, then the variance here will be just 1 minus the square of the expectation, simply because x squared is always equal to 1. Okay? Our starting point is a very classical inequality, the so-called Bakry inequality that can be formulated in many different ways, the spectral gap. But here I will give two forms of this Bakry inequality in terms of two different complex measures. The first one that I want to recall is the so-called influence. So you have a Boolean function on the n-dimensional discrete hypercube. Then the so-called influence of the ith variable of their function is defined to be the probability that the value of f changes when you flip the ith coordinate. So here again, the probability is with respect to the uniform probability. In other words, you can also define this variance here, the individual variance here, in terms of LP norms of your partial derivative operator. Let me recall that if I define this capital DI operator as a discrete analog of partial derivatives along the ith direction. So here, as before, this symbol of x plus I denotes the vector that I flips the ith coordinate of x without changing the rest of n-1 coordinates. Then this partial derivative capital DI is simply the 1/2 of f of x minus f x flipping I. This is a partial derivative operator, and you can easily compute that if your function here is a Boolean function, then this very definition of the influence of an ith variable can be rewritten as the piece power of LP norm of di of f. Simply because f here is a Boolean function taking values in plus minus 1, so di of f will take value in plus minus 1 and 0. So here you always have this very important identity that is very often used in many places about the Boolean function. So no matter which p you choose, the piece power of LP norm of di of f is always the influence. Okay. So here I define this for Boolean functions. You can also define it for functions taking values in real numbers. Then you need to choose among these several expressions, so which you want to use to define the influence. For a general function, then the so-called Bakry inequality can be written as follows. You consider any function on the n-dimensional Boolean cube. So first of all, we do not consider the Boolean function only. Then the Bakry inequality says that the variance with respect to the uniform probability measure is bounded from above by the sum of all these individual influences. We also call the sum of the individual influences the total influence. That will be recorded later. But here, this inequality is valid for all functions on the discrete hypercube. Then how do you define the influence, these individual influences? And here we are using the one that is defined in terms of square of L2 norm of di of f. Okay. If you define the individual influence in this way, it is valid for all functions. If you look at the Boolean functions, then immediately you have the following consequence. Okay. What this Bakry inequality tells you is that the total influence of this function has a lower bound that is variance. If you consider Boolean function, that is so-called balanced. Balanced means you have half a probability taking values in plus 1, half probability taking value in minus 1. Then in this case, your variance is always equal to 1. That is a lower bound of the sum of these individual influences. So as a consequence, there exists always some variable whose individual influence is at least 1 over n. This is a very simple consequence of Bakry inequality. By the way, this Bakry inequality, even if you restrict it to the Boolean functions, is sharp, which can be seen from the dictatorship. Okay. A surprising theorem by Kelly and Linnell in 1988 said that the previous consequence is actually not optimal. You can do better. Namely, you can always find some variable for balanced Boolean, any balanced Boolean function, such that the individual influence of this variable is actually at least of the order logarithmic of n divided by n up to a universal constant. By universal, I mean this constant does not depend on dimension. And this is a significant improvement of the Bakry inequality because recall that any Boolean function eventually gives you a voting scheme. If your Boolean function is balanced, means this voting scheme is fair. So a consequence of this KKL theorem tells you that in this fair election, you can always find a variable that has influence at least the log of n over n. In other words, it's possible for you to find a small group of people. If you could somehow convince those people to change their mind during the election, then you have an influential effect for the election that is much more than you could expect. So you have a 1 over n order of people, but the influence is actually log of n over n. So in other words, every balanced Boolean function has an influential variable. That is what the KPL theorem tells us. Okay? Any questions so far? Then you may ask whether this log of n over n is optimal, and this is indeed the case. That can be captured by the previous tribe function by choosing this S of t suitably. So you have n people, and you divide it into S and S tribes. Each tribe has t people, where if you choose this t to be something like log n over log of n minus log n, then essentially you can compute that the maximum individual influence is essentially log n over n. So that captures the optimalness of this KKL theorem. So we have seen Poincare inequality. We know it is sharp for indicators, but we also see this KKL theorem as a tightening of the Poincare. Well, this KKL is sharp for the type function. Also, you can check that it's not sharp for the majority function. So, although these two inequalities are sharp, have very interesting consequences, they are not optimal for most interesting examples. So maybe there is still some way to tighten this Poincare inequality in a different way, and that is the second tightening of Poincare that I want to recall here. This time I want to rephrase this Poincare inequality in a different way, using a different complex measure, the so-called sensitivity. So what is sensitivity? You consider Boolean function. For example, you can consider this Boolean function on this three-dimensional Boolean cube. Okay, in other words, you have this n that is equal to 3, then these values over the index give you a very specific example of Boolean function. Then what is in sensitivity? The sensitivity is a local concept. You look at some point, for example, this red point in this three-dimensional Boolean cube, then the sensitivity of this example Boolean function at this point of x is defined to be the number of coordinates such that the function of f has different values when you flip your ice coordinates. So what does it mean? It means that from this picture, for this example of Boolean function at this point, you look at the neighbor of this red point, which is this collection of 3 blue points that has value +1, +1, and the -1 here. Then you compare your original value of your function at this point and the value at these neighbors. Okay, there are two neighbors that have different value though. So the sensitivity of this example at this point is equal to 2. That is the sensitivity. And if you compare with the previous notion of influence, the influence is essentially computing something similar but from a different perspective. The sensitivity, the influence is actually computing same guy but from in terms of directions. For example, for this 3n-dimensional Boolean cube, you have 3 directions, you have 3 coordinates. For example, if you look at the coordinates that corresponds to this green direction, you have 4 pairs of points. Then you look at the number of points where the function have different values. That is how you define the individual influence. For example, for these 4 pairs, you have -1, 1 here, so they have different values. You have -1 here, +1 here, so you have different values. The same is true for this pair of points along this direction, but not for the last one of -1 here and -1 here. So if you compute the individual influence corresponding to this direction, of this green direction, you have 3 out of 4 pairs that have different values. Then the individual influence, according to the previous definition, is equal to 3 over 8. 3 over 8. But when you compute this sensitivity, you are actually computing these different values with respect to the neighbors. So if you look at globally of these two quantities, there is this natural relation. Namely, if you consider the expectation of this sensitivity defined here with respect to the uniform probability measure, that is exactly the total influence, which is the sum of the individual influences. So this natural relation you can verify, you can check this for this example on the three-dimensional Boolean cube. So in other words, the previous Poincare inequality can be rewritten in the following way. The variance has an upper bound. The upper bound, we know it is equal to the total influence. Now we use this average of the sensitivity as a lower bound, as upper bound. Okay, so this is another way to write this Poincare inequality. And now I want to tighten this Poincare inequality in terms of the sensitivity. Any questions? Okay, a very natural tightening given by Talagrand in 1993 is as follows. So recall that sensitivity is at each point is some non-negative integer. So obviously the square root of h of f is always bounded from above by h of f. Then this tightening by Talagrand says the following: you consider any Boolean function on an n-dimensional Boolean cube, then the variance is bounded from above. This time you do not consider the average of sensitivity, but the average of the square root of sensitivity. Then you have an additional constant that is dimension free. Okay, so this is another way to strengthen the Poincare inequality, and you can verify that this inequality, in some sense, is optimal for the majority function that we reviewed from the very beginning, but not for example, the tribe functions. To summarize, we have now two tightenings of the classical Poincare inequality from different perspectives. The KKL in terms of influence, the Talagrand inequality that is in terms of the sensitivity, and they do not imply each other. So the natural question is whether you can find a unifying tightening of both the KKL and the Talagrand inequality. So that was a question asked by Talagrand in 1997. And he actually has a very explicit guess for these inequalities that may not exist here. And he has a motivation. Let me first review what he has done in 1997. So he observed that he can prove the following thing. We discussed three notions: the variance, the influence, the sensitivity, and he could somehow relate these three quantities into the following inequality. There exists some alpha between 0 and 1/2, together with a universal constant c, such that the following inequality holds. So if you compare with the previous Talagrand inequality strengthening Poincare, you still have this expectation of the square root of sensitivity on the left-hand side. Now the lower bound, apart from this variance, together with this universal constant, you have also some strange terms, essentially some weighted geometric mean of some logarithmic stuff, logarithm 1 over variance and logarithmic something divided by this W of f. Well, what is this W? W over f is the sum of a square of the influence instead of the total influence. So there is this very strange term. And he could prove, so he could prove that this is true for some alpha between 0 and 1/2. Actually, his proof does not work for the extreme point alpha being 2. And
alpha 1/2.
Okay, so this is 1/2. The typo here, this should be 1/2. And he actually already proved the case, the other endpoint case alpha being 0, already in the paper in 1993. So the conjecture is that maybe this inequality is true for alpha being 1/2. Okay. So let me address it. If you have alpha being 1/2, then this term of logarithmic of 1 over variance disappears. You have only this term in terms of this W. So the inequality looks nicer. Also, since this is essentially some geometric mean of these two terms, if you could prove this for alpha being 0 and 1, alpha being 1/2, then you actually prove it for any alpha in between. So the better this, so the larger this alpha is, the result becomes stronger. So that is kind of the story behind today's talk. So he conjectured that this inequality, which I denote by T alpha in general, he conjectured that this inequality is true for the endpoint of alpha being 1/2. And this was resolved by Eldan and Gross recently using the stochastic analysis, which is surprising to the community because very often in the past or or a classical way of proving such functional inequalities on the Boolean cubes. Very often use some free analysis techniques like hypercontractivity, which is very much based on the analysis of semigroups. So, so if you look at the paper, then they actually emphasize that, okay, this is proof that bypasses the use of hypercontractivity stuff. So this is the result, but actually it proves something more, but I will focus on this very specific result by Eldan and Gross, namely this inequality when alpha being 1/2. And up to now there are several alternative proofs. I will just list what I know, including contribution to some people sitting here. And the main result of this talk is, roughly speaking, a semigroup of this inequality that extends to more general spaces. Okay, I will explain what these spaces are. But first of all, this is a proof that uses semigroup. So let me recall the semigroup that we are going to use on the discrete hypercube. This was already mentioned in some of our previous talks. This is the so-called free expansion of any function on the Boolean cube. Any function can be represented uniquely as a linear combination of the characters that is labeled by S. This S here is a subset of the first and positive integers, and each chi-S is the product. This is a function that takes any vector in the Boolean cube to the product of the coordinates xi, where I belongs to S. You can verify this from the basis. Then you have the free expansion. Then this heat semigroup is defined as follows. It takes each character, it's a linear operator that takes this character chi-s to a multiple of itself, with this multiplication factor to be e to the negative t times the cardinality of f. So this is the definition of the heat semigroup in the statement of the theorem here. Okay, let me emphasize that the proof is essentially the key ingredient in this proof was more or less contained in the previous known work. Okay, but we want to emphasize that this argument actually extends to more general spaces, which I will recall in a second. Before that, do you have any questions? So, what are these spaces? I will not give a very precise definition here. The crucial point behind this is a theory named after Bakry and Émery that characterized the Ricci curvature lower bound of a Riemann manifold. Roughly speaking, in this theory, the Ricci curvature lower bound of a manifold, so say that this Ricci curvature lower bound is this real number k, positive or negative, is equivalent to the following condition, so-called Bakry-Émery curvature dimension condition, that has nothing to do with the Riemannian structure. Okay, I will explain this in detail, but the whole point is, in this condition, you don't see anything about Riemann manifold, and this condition is formulated in terms of this inequality, which we usually call the gamma 2 condition. Here, these two operators, or actually bilinear forms of gamma and gamma 2 are defined as follows. You first have a semigroup. Okay, you first have a semigroup. In this case, it is a heat semigroup generated by the Laplacian on the Riemann manifold. Then, using the generator of the semigroup, you can define the so-called Gary-Duchamp, this gamma, as follows. It takes any two nice functions, say f and g, to a real number, and the definition is as follows. This takes two functions to a function, and the function is defined as follows. So twice of this gamma of f of g is defined to be the following thing. You apply the generator to the product of f and g, you subtract by generator acting on f, multiplied by g, and symmetrically f times Laplacian of g. So this definition might be weird if you see it from the very beginning, but roughly you can understand this Gary-Duchamp, this gamma operator, as the first order derivative stuff along the heat flow, along the semigroup flow. And the next operator, the next bilinear form gamma 2 can be understood as a second order derivative along the heat flow, whose definition is very similar. The difference is that, okay, twice of the Gahi-Duchamp, the gamma 2 of f and g is a function that is defined as follows. Instead of taking the product of f and g, you take the gamma of f and g that is just defined. Then you define in a very similar fashion, and this is the so-called gamma 2. And the beautiful thing is that this inequality comparing these two bilinear forms characterize this geometric condition of the Riemann manifold. Starting from this, you can define the Ricci curvature lower bound without the use of the Riemann manifold structure, since this condition only requires a very nice semigroup, which I will not recall details. Okay. For example, you can consider the Orton-Stein-Uhlenbeck semigroup acting on the Gaussian space. Okay. I will only mention this example as very often when you have a result for Boolean functions on discrete hypercubes, you can ask the Gaussian analog in the Boolean analysis. So I will just mention this example only. So what does it mean? It means that you can define the Ricci curvature lower bound for this Orton-Stein-Uhlenbeck semigroup in a similar fashion. You use this generator here, which is now Laplacian minus x times the gradient. Then you play with the same definition. You define the Gahi-Duchamp, you define the gamma 2, then you formulate this condition, the gamma 2 condition, then you can verify that, okay, in this case, the Ricci curvature lower bound is one that is sharp. And starting from this, you can derive a lot of interesting things, like the hypercontractivity, like the isoperimetric inequality, and this is within the scope of the Bakry and Émery theory. Okay? Any questions? But this is based on some nice assumption of the underlying Markov semigroup, which somehow is missing for certain examples on discrete spaces. For example, for the heat semigroup that we record on the discrete hypercube, you can define the Ricci curvature lower bound in the similar way. You can derive still something, but not everything. Okay, this is because of the discrete structure, discrete space structures, you like some nice general identity here. So, for example, you cannot derive hypercontractivity on the Boolean cubes using this definition. So, actually, our main results, which I will state in the following, has two parts. One for the semigroup that is nice, one for the semigroup that is not nice, which is often the case for discrete spaces. But before stating the result, let me recall this inequality T1/2 again, because we want to prove something like this for more general spaces. But how do you define these three quantities? The variance, the sensitivity, and the influence. The variance is not difficult. You only need the probability measure, which is the reference measure for the semigroup. So this is easy to define. But how about the influence and the sensitivity? Well, for the sensitivity, we define this to be the numbers of the neighbors of this point where your function have different values. You can also verify that this is equal, the sensitivity is actually equal to the square of the gradient. A square of the gradient is defined to be the sum of the partial derivatives, the sum of the square of the partial derivatives. Okay? And it's very natural to relate this square of the gradient to the Gahi-Duchamp. Okay, you can actually verify this for a lot of examples. So in other words, in the more general framework of Bakry and Émery, it's very natural to take Gahi-Duchamp, this gamma of f, to replace this sensitivity here. And this time we will only need a very nice semigroup. We can use a generator to define this Gahi-Duchamp, this gamma of f, so we can define the sensitivity in this context. Similarly, the influence can be defined in more general spaces as well. So recall that the sensitivity, the influence, individual influence, can be defined to be the piece power of the LP norm of this partial derivative di acting on f. Here in particular, we are going to choose the L1 norm of di of f to define the influence, but this partial derivative operator is actually not so helpful when it comes to more general spaces. So may you observe the following thing, that di of f on the Boolean cube, whose definition is here, is actually the difference between f and the conditional expectation of f with respect to the ith variable. So that is still something that you can verify. And we are going to define the influence, individual influence on more general spaces that we are going to discuss using this expression. So L1 norm of f subtracting conditional expectation with respect to the ith variable. For example, for the Gaussian space. So having this, we can state our main result if you define the sensitivity and the influence as above, so that you can talk about them for more general spaces as long as you have a good semigroup. Then this inequality by Talagrand when upper being 1/2 is valid when you replace the Boolean cube with, first of all, probability measures that have nice semigroups, such as a Gaussian space with Haonan-Uhlenbeck semigroup, admitting a reciprocal lower bound in the sense of Bakry and Émery, and we require this lower bound to be strictly positive, which is very often the story in this picture. But as I said, I assume some nice property, something like a chain rule, to be true, and unfortunately this will exclude some discrete examples, such as the discrete hypercubes. So even this result, which is very general, on one hand, does not include the ±1, the discrete hypercube. That is the starting point of the story. So another part of the result says, okay, the result actually works for more general discrete spaces, among which we select these biased discrete hypercubes as typical examples, which means I still have ±1 as my underlying space, but the probability measure is replaced by the biased probability measure. It has probability p at 0.1 and it has probability 1 minus p at -1, with p being any real number between 0 and 1. Yes.
So on the first example, you're really replacing -1, 1 or -1, 1 to the end. So do you want the thing to be a product space always or not?
Yes, I always want this to be a product space. That's why I say just replace one of them by these. So in general, I should replace product n-fold product of ±1 by, for example, n-fold product of the one-dimensional Gaussian as well as n-fold product of the biased hypercube. So I'm always talking about the product space structure to talk about the dimension-free phenomenon. Okay. Any question about the main result?
So no gamma 2?
The gamma 2 is implicitly contained in this reciprocal lower bound stuff.
No, in the second.
In the second one. In the second one, I will explain this in the second. Why we do not talk about this in terms of reciprocal stuff or gamma 2 stuff. So on one hand, you can verify that gamma 2 is still satisfied for this biased discrete hypercube, but that is not the reasoning that we have this result. We have the result because the proving gradient for proving the continuous result is there for the discrete hypercubes. The reason is not for the reciprocal lower bound or gamma 2 stuff. Gamma 2 stuff is only to make the statement clean, which I will explain in the next slide. Okay, any more questions? So Sasha made a very good point. So the proving gradients are essentially as follows. Okay, you have, for example, from in the classical recurvature theory or the Bakry and Émery theory, whenever you have a nice lower bound for recurvature, say this lower bound is strictly positive, then you can imply hypercontractivity, for example, or the Bobkov inequality, actually the local version of this Bobkov inequality that I will recall in a second later. And let me recall that these two inequalities are very powerful in deriving some other very classical results, such as KKL. So this might be a little confusing, but to prove this KKL, the crucial ingredient is hypercontractivity. You certainly need some additional assumption for the semigroup, but maybe the hypercontractivity is the most important. Also, the Talagrand inequality can be seen from Ricci curvature lower bounds or from some Bobokov types inequality, etc. So the two tightenings of Poincare inequality that we mentioned from the very beginning have been already generalized in this very general framework of Bakry and Émery, and our main result can be understood from the same spirit. Within the same picture, we prove something similar, namely this inequality of T1/2 also follow from the Ricci curvature lower bound in the same sense. And the main ingredient, proving ingredient, is a combination of these two. Okay? Combining these two, you can prove T1/2. Actually, you can also prove T0, which I will recall later. I will explain later, but actually to prove this T0, you do not need, you only need some isoperimetric inequality or Bobokov inequality would be enough. So what I'm saying is that the extension of this classical functional inequality on Boolean cubes or for Gaussian space have been extended to more general Bakry and Émery framework. And here we are kind of extending this inequality of T1/2 in the same picture. But as Sasha said, why don't we see this Ricci curvature condition in the discrete example? Because the crucial proof ingredients are these two hypercontractivity and a local Bobokov inequality in the middle. The assumption of Ricci curvature lower bound is just to make the statement clean. Okay, I don't want to assume that we have this and that we have the final result. It is actually very standard to have Ricci curvature lower bound as one main assumption, then you derive what you can say. So in the discrete setting, like the Boolean cubes, you may still talk about gamma 2 or Ricci curvature, but this implication from here to here is missing. For example, you can verify classical Boolean cube, you have Ricci curvature lower bound that is positive, but this does not imply hypercontractivity. So the story stops here, but you can still prove the same result because the two main ingredients in the middle are still there for the discrete spaces, such as the biased hypercubes. So that's why the statements of two results in two different settings are kind of different, but essentially the main ingredients are these two tools in the middle.
So do you know examples where you only have Bobokov but not hypercontractivity?
Oh, that one I don't know. So this is also a very good point. Here I'm not going to talk about the relation between hypercontractivity and a local Bobokov. So maybe there are some results that derive one from the other, or maybe they're equivalent. I roughly recall some results relating hypercontractivity of isoperimetric inequality, which is very much related to the local Bobokov that I'm going to talk about. So maybe this implication is also confusing here. There are some potential connections in between. Yeah. Any other questions?
And can you think of some sort of other inequality which will work in discrete spaces?
Other inequalities or other examples?
Like instead of doing the proof twice, can you maybe change something and do the proof once?
I'm sorry, you want to change?
Instead of doing the proof twice, once for the continuous spaces and once for the discrete spaces.
You want to do them simultaneously? It is actually possible. Roughly speaking, the proof for the discrete space should also work for the continuous space, but not the other way around sometimes. So, more questions or comments? So the rest of the time will be devoted to expanding these two ingredients. First one being the hypercontractivity, which is a very classical result, which and Gross, seeing that the heat semigroup that we defined from the very beginning has the following property. We know this semigroup is always contraction over LP when P is between 1 and infinity, and hypercontractivity tells you that it is actually contraction from LP to LQ with P and Q as well as the time t satisfying the following relation. P is bigger than 1, smaller than Q, and the time t satisfies this condition that is optimal. But in the following, we actually only need the case when Q is equal to 2, which is very often the case in the application to Boolean functions. So, as a consequence of this hypercontractivity, we have the following two estimates, which are kind of the standard. The first one says that for any t, and for any function, not necessarily Boolean, the variance of pt of f has this upper bound. This upper bound is really the geometric mean of the variance of f, so variance of pt of f at time 0, together with another part which is exactly this w of f, which is a weird part w of f appearing in the inequality T1/2. The second estimate, second corollary of this hypercontractivity is that for Boolean functions, the variance of pt of f is bounded by this power of variance of f. It's crucial to have this additional power that is strictly bigger than 1. So here, this theta of t is defined as here. So the theta of t is just the number that I can use Hausdorff's inequality for together with this hypercontractivity. Okay, so this is the first ingredient. Any questions?
So for this, you don't need the optimal time for the hypercontractivity.
Yes, you can also say that the previous statement for the ingredient of hypercontractivity can be actually very general. So maybe you do not need that strong result. You don't need a very optimal result of hypercontractivity to derive such a result. Yes, and in some sense, you can also extend the result to more general spaces where you don't know the optimal time. Okay, the optimal constant in this inequality 1/2 is not important to us. We only need this constant to be dimension free.
The first one is very easy, right?
This one?
Yeah, just hypercontractivity.
I think the second one might be easier, but yes, the first one is also to apply hypercontractivity and use some Martingale property, which relies on the product structure of the space. Okay, the second ingredient. When I first see the proof by Belgium, Madrid, and Ivanisvili, it took me some time to understand. Okay, but my understanding is that this inequality in the following is actually better to understand in the continuous framework instead of Boolean cubes. So let me recall the Gaussian isoperimetric profile that is already discussed in previous talks. This is a function from 0,1 to 0 to 1 over square root of 2 pi that is defined as follows. You have little phi that is density of standard Gaussian, and capital phi is a probability distribution function for little phi. Then you define the isoperimetric profile in the following way. Then this local Bobokov inequality can be derived from Bobokov and Gusser, and this is actually we learned from previous works, and whose proof inspired the p-bias cubics using some Ricci representation theorems and stuff. So this theorem of Bobokov and Gusser is very general. It works for arbitrary probability spaces, arbitrary probability measures. In their result, you don't see the semigroup here, but you play with some trick, then you can prove the following inequality. So here, h is a function, is a Boolean function that takes values in 0 to 1, which will be easier to formulate. You can, very often, this h is taken to be the characteristic function over some set. Then you have the following estimate. As parametric profile of pt of h is bounded from above by this quantity times semigroup acting on this this absolute this gradient of h is essentially the square root of the Bakry-Duchamp, but let's take the gradient form here. Then from this, using the elementary estimate of isoperimetric profile, you have the following corollary, which is another ingredient of the proof. So, namely, you have the difference between the variance of f and the variance pt of f that is bounded by some quantity, some scalar multiplying the expectation of the square root, expectation of this is actually the square root of the sensitivity, okay, square root of sensitivity. And in particular, when you send the t to infinity, okay, you can either take t to infinity in the above local Bobkov's inequality or the following corollary, then you get something that is very similar to the isoperimetric inequality. So what we need is actually this local variant. We need a time t to be finite. We do not want this t to go to infinity, which is more often to be used. So this is the second proving gradient.
So the functions in the corollary are going to minus 1, 1.
Yes, here you have 0 to 1, and here you have plus minus 1. Here you have 0, 1 because the formulation will be cleaner, and this is very. So in general, you actually have an additional term inside the pt. You have a square root of this part plus something in terms of isoperimetric I of h, but since h takes values in 0 and 1, so that part vanishes because I here vanish at the endpoint 0 and 1. So if I do not take h to be a function taking value in 0 and 1, instead if I take h to be a function taking value in plus minus 1, the inequality will look more ugly. And from here I jump to f, taking value in plus minus 1, that is what I need, and you can see from this lower estimate of I here, because from h to f you just do some linear rescaling, linear transformation. That's why you have the 1/2 here, and that's why. So that is the connection between these two. I just choose h to be 0 and 1 value because the inequality looks nicer. Okay. Yeah.
1 second. With inequality for all h, etc., is it just point-wise inequality?
Yes, that is a crucial thing. Here it is actually a pointwise inequality. When you send t to infinity, you can verify that pt of a function f will go to the expectation of f with respect to uniform probability measure, and that's why you get not pointwise inequality. You have an integral inequality. But yeah, this pointwise inequality is stronger. That's what we need. Any more questions? So the proof is as follows. Let me first give a proof sketch for the inequality in T0. That is easier, that was already known in 1993. You first give a lower bound of the left-hand side. Recall that the square root of sensitivity is exactly the gradient of f. Then you first use a lower bound that we know from here. Okay, this is a lower bound in terms of t. Okay, we need a finite time in t. Then you continue. You first use this corollary of local Bobkov. Then you use this lower bound, and then you use this upper bound of variance of pt of f. That is corollary of hypercontractivity. Here we use this upper bound that is for the Boolean functions instead of the upper bound in terms of w something. And if you continue, you get variance times this quotient, then compare with this T0 inequality that suffices to prove this quotient to be bounded from below by the square root of logarithmic term. And you can achieve this by choosing a very special time of t, which I skipped the details here. If you choose a finite time t in a clever way, you get this lower bound. But this is actually a very complicated proof of this inequality. I will give you a shorter proof of this without using hypercontractivity, without this nothing argument. But this is complicated proof of T naught actually instead of what you do for T1 half. For T1 half, you follow the same strategy. You get a lower bound of the expectation of the sensitivity by this corollary of local Bobkov. Then this time you use the upper bound of variance of f in terms of this W stuff. And you need this in the end anyway. So if you continue, you still have this variance of f as a common factor. The rest is to estimate this quotient from below by this logarithmic square root of logarithmic term in terms of W. So you know it suffices to prove this inequality, which is very similar to the previous one. This time you still choose a very special time of t to achieve this. But you may ask, okay, here you have a function on the left-hand side of W of f divided by variance, but on the right-hand side you only have a function of W. So here you also need to compare these two quantities, W and the variance, and you need to use the result of T naught. What does this mean? It means the T naught in the T naught inequality, here you don't have W here, you have a variance. So from this, you know that if the W term here, if it is too large, then this inequality will hold automatically, because you know this is true if you replace by variance. If it is large, if it is very large compared to the variance, you know this is true. So it suffices to prove this inequality when this W term is small compared to variance, and that's why you can achieve this inequality by choosing a finite t. So this is a quantity involving two terms on the left-hand side. So that's basically the proof. And let me finish with one remark about this inequality of T naught. As I said, the previous proof of T naught is very complicated because you can just derive it immediately from the isoperimetric inequality, which is a limiting case of a local Bobkov. You send t to infinity, you get this isoperimetric type inequality, and out of this you can already finish the proof of T naught because the variance is exactly x log x times 1 minus x, with x being the expectation, and you actually can use a better estimate of the Gaussian isoperimetric profile. Previously we used a lower bound in terms of quadratic function, but you know this lower bound in terms of this very strange function. That is exactly what we need in this inequality of T naught. So out of this you can already finish the proof of T naught without using hypercontractivity, without a local version of anything. But the crucial thing is that the proof of T1 half is more local. So it's better to finish the proof of T naught using some local argument, which means I choose Pt for finite t instead of sending t to infinity, if you want to prove T1 half in a similar way. Okay. Any questions? So if not, then I will stop here and thank you very much for